2 trillion galaxies blaze across the observable universe. Each one holds hundreds of billions of stars. Right now, 90% of them are completely invisible to us, hidden beyond the reach of even our most powerful telescopes. We stand at the edge of cosmic discovery, about to witness galaxies that defy every rule we thought we knew. Galaxies where gas burns brighter than 1 trillion stars. Dead galaxies spinning faster than anything alive. Galaxies shaped like eyes, dolphins, and perfect rings floating in absolute darkness. For decades, astronomers believed they had counted the universe, 100 billion galaxies. That number appeared in textbooks, documentaries, and scientific papers. It seemed almost incomprehensible. 100 billion island universes, each containing billions of stars, scattered across the void. We thought we understood the scale of everything. We were catastrophically wrong. In 2016, a team led by Christopher Consolis examined deep space images captured by the Hubble Space Telescope. They converted these images into 3-dimensional maps, measuring galaxy populations at different points in cosmic history. Then they used mathematical models to account for galaxies too distant and faint for any telescope to detect. What they discovered shattered our understanding completely. 2 trillion galaxies fill the observable universe. Not 100 billion, 2 trillion. The universe contains 10 times more galaxies than every estimate we had trusted. Think about that number for a moment. 2 million separate collections of stars, gas, and dust. If you counted one galaxy every second, it would take you over 63,000 years to count them all. The implications hit immediately. 90% of all galaxies in the universe remain completely invisible to us. They exist beyond the detection threshold of even our most sophisticated instruments. Too far away, too faint, too ancient. We have barely glimpsed 1/10 of the galactic population surrounding us. The cosmos suddenly became 10 times larger, 10 times stranger, 10 times more filled with possibilities we cannot yet imagine. These galaxies are not evenly distributed across time either. When researchers looked backward through cosmic history, they found something unexpected. The early universe, when it was only a few billion years old, contained far more galaxies packed into each region of space than we see today. Small galaxies dominated the ancient cosmos. Over billions of years, they merged together, colliding and combining to form the larger galaxies we observe nearby. This discovery explains an ancient puzzle that troubled astronomers for centuries. Olber's paradox asked a simple question with a troubling answer. If the universe is infinite and filled with stars, why is the night sky dark? Every line of sight should eventually hit a star, making the entire sky glow as bright as daylight. The answer lies partly in cosmic expansion and partly in this revelation. There are so many galaxies that every point in the sky does contain part of one. However, the combination of expanding space, light-absorbing dust, and the finite speed of light keeps most of them hidden in darkness. The future visibility limit adds another layer of strangeness. Because the universe's expansion is accelerating, driven by the mysterious force we call dark energy, galaxies are racing away from us faster and faster. Eventually, light from the most distant galaxies will never reach Earth, no matter how long we wait. In principle, we could theoretically observe about 2.3 times more galaxies in the infinite future than we can see right now. But in practice, redshift will make them fade from view long before that happens. Consider what this means for our place in existence. We live in a universe containing 2 trillion separate galaxies. Each galaxy holds an average of 100 billion stars. That gives us roughly 200 billion trillion stars in the observable universe alone. And remember, the observable universe represents only the portion of space close enough for light to have reached us since the Big Bang. The total universe could be vastly, incomprehensibly larger. James Webb Space Telescope observations continue to push our detection limits deeper. Every new survey reveals galaxies we missed before, faint dwarf galaxies, Ancient galaxies from the universe's first billion years. Galaxies in the zone of avoidance, hidden behind the dust and stars of our own Milky Way. The count keeps rising. What secrets hide in that 90% of galaxies we cannot yet see? What strange physics governs their formation? What types of stars fill their cores? We stand at the threshold of discovery, knowing that everything we have learned about galaxies comes from studying only 10% of them. The sheer abundance staggers the imagination. 2 trillion opportunities for planets. 2 trillion chances for chemistry to create something unexpected. 2 trillion laboratories where gravity, light, and matter interact in ways we are only beginning to understand. And we have examined closely only a tiny fraction of that cosmic collection. But quantity tells only part of the story. What matters more is the incredible diversity hidden within those 2 trillion galaxies. Each one is unique. Each one follows a different evolutionary path, and some of them are so bizarre, so far outside our expectations, that they force us to rewrite the rules entirely. The galaxy types we are about to explore will challenge everything you think you know about how the universe works. Galaxies come in 3 basic shapes, each telling a different story about cosmic evolution. Spiral galaxies, elliptical galaxies, irregular galaxies. Understanding these categories is like learning to read the universe's architecture. Every galaxy fits somewhere within this classification system, though some push the boundaries in spectacular ways. Spiral galaxies are the most dramatic. They look exactly like their name suggests. A central bulge surrounded by sweeping arms that curve outward in elegant patterns. Our Milky Way is a spiral galaxy. So is Andromeda, our closest large neighbor. These galaxies rotate, with their arms trailing behind like water swirling down a drain. The arms are not solid structures. Stars, gas, and dust move in and out of them over millions of years. The arms persist because of density waves, regions where gravity temporarily compresses material into glowing concentrations. Spirals are stellar nurseries. Gas and dust collect in the arms, compressed by their passage through these density waves. That compression triggers star formation. Hot young stars ignite, flooding their surroundings with ultraviolet light. These newborn stars appear blue, making spiral arms shine with brilliant azure hues. Meanwhile, the central bulge contains older, redder stars that formed long ago when the galaxy was young. A faint halo of ancient stars surrounds the entire structure, extending far beyond the visible disk. About 60% of all galaxies in the universe are spirals. They represent the home of most stars in existence. But spirals come in varieties. Normal spirals have arms that emerge directly from the central bulge. Barred spirals, which make up about 2/3 of all spirals, have a straight bar of stars cutting across their center. The arms connect to the ends of this bar, rather than to the bulge itself. The Milky Way is a barred spiral, so is Andromeda. Scientists believe the presence of a bar indicates that a galaxy has reached full maturity. Spirals can be further classified by how tightly their arms wind. Some have large, luminous bulges with arms coiled tight, like a watch spring. Others have small bulges with loose, open arms. Luminous stars and glowing emission nebulae are especially prominent in the loose-armed varieties. Our galaxy falls somewhere in the middle of this spectrum. Elliptical galaxies look completely different. They range from nearly perfect spheres to elongated footballs. No arms, no disk, no obvious structure at all. Just a smooth, featureless ball of stars. Ellipticals contain very little gas and dust, which means they form almost no new stars. The stars they do contain are ancient, old, red, moving in random orbits around the galactic center, rather than in organized rotation. The lack of star formation makes ellipticals appear dim compared to spirals of similar mass. They lack the brilliant blue young stars that make spirals so visually striking. However, Ellipticals come in an enormous range of sizes. The smallest dwarf ellipticals contain only a few million stars and stretch just a few thousand light-years across. The largest giant ellipticals are monsters, containing over 100 trillion stars and spanning hundreds of thousands of light-years. These giants form when multiple galaxies merge together over billions of years. Elliptical galaxies represent about 33% of all galaxies in the universe. Scientists believe many of them form through galactic collisions. When two spiral galaxies crash together, their organized structures get scrambled. Stars are flung into random orbits. Gas clouds collide, triggering intense bursts of star formation that consume all available fuel. What remains is an elliptical. The stars in an elliptical can be packed so densely near the center that the core looks like a single giant star. If Earth were inside an elliptical galaxy, the night sky would blaze with the light of surrounding stars. No darkness, no night. Irregular galaxies are the misfits. They have no defined shape, no symmetry, no clear structure. They look chaotic, disorganized, like someone threw stars and gas into space randomly. Many irregulars are small, containing relatively few stars. The large and small Magellanic Clouds, visible from Earth's southern hemisphere, are classic examples. They orbit the Milky Way as satellite galaxies. Irregular galaxies often show intense star formation activity. Unlike ellipticals, which have used up their gas, irregulars contain both old and young stars mixed together. They have plenty of gas and dust to fuel new stellar birth. Their chaotic appearance often results from gravitational interactions with larger neighbors. A small galaxy passing too close to a massive one gets stretched and distorted by tidal forces. Sometimes the interaction is so severe that the smaller galaxy is completely torn apart. About 10% of known galaxies are irregular. However, this percentage was much higher in the early universe. As time passes, irregulars merge with each other or with larger galaxies. They gradually disappear, absorbed into the growing population of spirals and ellipticals. The irregular galaxy population has been declining for billions of years. These three categories seem simple enough. Spirals have arms, ellipticals are smooth balls, irregulars have no pattern, but nature loves to create exceptions. Some galaxies blend features from multiple categories. Others exhibit structures so bizarre that they defy easy classification entirely. Lenticular galaxies, for instance, have a central bulge and disc-like spirals, but no arms. They resemble fading spirals that have exhausted their gas supply. The classification system was developed by Edwin Hubble in 1926. He organized galaxies by appearance, creating what became known as the Hubble sequence or tuning fork diagram. Ellipticals on the left, spirals branching into two paths on the right, with lenticulars in the middle. For decades, astronomers hoped this sequence represented evolutionary stages. Maybe ellipticals evolved into spirals, or spirals into ellipticals. That hope proved false. Galaxies do not follow a simple linear evolution. Their life stories are far more complex, shaped by collisions, mergers, and the mysterious influence of dark matter. Modern observations reveal that galaxy type connects to environment. Spiral galaxies dominate in less crowded regions of space. Ellipticals cluster together in dense galaxy groups and clusters. This suggests that interactions between galaxies play a major role in determining their final form. Isolation allows spirals to maintain their delicate structures. Crowding leads to collisions that create ellipticals. Understanding these three fundamental types gives us a language to describe the cosmic zoo. But knowing the categories is just the beginning. Some galaxies push these definitions to their absolute limits. Others break the rules so completely that they force us to invent entirely new categories. The journey into galactic extremes begins with galaxies that should be impossible. Galaxies that have died. Max 2129-1 spins in the darkness, rotating twice as fast as the Milky Way. Its disk contains 300 billion stars. Massive. ancient, utterly lifeless. No new stars have formed there in billions of years. The galaxy is dead. This discovery defied everything astronomers expected. Dead galaxies should not exist in this form. When a galaxy stops forming stars, scientists believed it had to be an elliptical. The thinking made sense. Ellipticals form from violent collisions between galaxies. Those collisions scramble the organized structure, consume all the gas in explosive bursts of star formation, and leave behind a smooth ball of old stars. Dead galaxies were supposed to be shapeless, chaotic, the wreckage of cosmic crashes. Max 2129-1 shatters that assumption completely. It has a disk, it has rotation, it has the structure of a living spiral galaxy, but it contains almost no gas, no dust, no regions of active star formation, just old stars, spinning in organized orbits, inside a galaxy that looks like it should still be alive. The stars themselves tell a strange story. They formed early in the galaxy's history, when the universe was much younger, all at once, in the original disk, not from mergers with smaller galaxies. Then something happened. The gas supply shut off. Star formation ceased. The galaxy entered a state of suspended animation, slowly aging as its stars burned through their fuel with nothing to replace them. How does a massive disk galaxy internally rearrange itself as it ages without colliding with other galaxies? That question has no clear answer yet. Max 2129-1 suggests that galaxies can die from internal causes, not just external violence. Maybe the central supermassive black hole activated, generating powerful jets that blew away the remaining gas. Maybe the galaxy simply exhausted its fuel supply, having converted every available cloud into stars during its youth. Dead galaxies make up a significant fraction of massive galaxies in the universe. They appear red in color because they contain only old stars. Young blue stars, which burn hot and bright, have already died in supernovae or faded into white dwarfs. What remains are cooler red and yellow stars with lifespans measured in tens of billions of years. These elderly stars will continue shining for ages, but the galaxy as a whole has stopped evolving. It is frozen in time. Another dead galaxy, XMM 2599, formed when the universe was only 1.8 billion years old. It created over 300 billion times the mass of our star in stars, then abruptly stopped. At its peak, it was forming over 1,000 new stars every single year. Our Milky Way forms approximately 1. XMM 2599's furious star formation consumed its entire gas supply in less than 1 billion years, leaving it dead before the universe reached its second birthday. Why did it stop so suddenly? Models predict that massive galaxies in the early universe should be actively forming stars. Finding one already dead challenges our understanding of galaxy evolution. The galaxy may have stopped getting fuel from the surrounding cosmic web, or its central black hole may have turned on, heating the gas and preventing it from cooling enough to collapse into stars. Either way, something killed it in its prime. These dead galaxies rarely exist in isolation. Many of them sit at the centers of galaxy clusters, surrounded by smaller galaxies still forming stars. The dead central galaxy often shows signs of past cannibalism, having absorbed multiple smaller neighbors over billions of years. Yet despite eating other galaxies, it remains dead. The gas from those consumed galaxies somehow never reignites star formation. The concept of galactic death is more nuanced than it first appears. A galaxy can be mostly dead while still having tiny pockets of star formation. A few gas clouds might survive near the edges. A minor merger with a gas-rich dwarf galaxy might trigger a brief flare of activity. But the overall trend is toward darkness. The galaxy gradually transitions from blue to red as its last young stars die and nothing replaces them. Astronomers classify galaxies by color to track this process. Blue galaxies are alive, actively forming stars. Red galaxies are dead or dying, dominated by old stellar populations. Green galaxies sit in between, transitioning from life to death. This green valley represents a critical phase in galactic evolution. Something is happening to galaxies as they cross it, something that permanently ends star formation. The frequency of dead galaxies increases as we look at the nearby universe compared to the distant past. In the early universe, almost every galaxy blazed with star formation. The cosmos was younger, gas was more abundant, and conditions favored stellar birth. As billions of years passed, more and more galaxies crossed into death. Today, a large fraction of massive galaxies are red and dead. The universe is slowly fading. This progression has profound implications for the far future. Eventually, billions of years from now, almost every galaxy will be dead. The last generation of stars will have formed. The night sky will dim as those stars age and die with nothing to replace them. The universe will enter an era of darkness, illuminated only by the fading embers of ancient stars and the cold radiation of black holes. Dead galaxies also provide natural laboratories for studying stellar evolution without the complicating factor of ongoing star formation. When you observe a living galaxy, you see stars of all ages mixed together. Young, middle-aged, and old stars shine side by side. In a dead galaxy, all the stars are old. You can study how stellar populations age without new generations confusing the picture. Some dead galaxies show evidence of past violence, even though they currently have smooth, elliptical shapes. Deep observations reveal faint streams and shells of stars in their outer regions. These features are the remnants of smaller galaxies that were torn apart and consumed. The gravitational ripples from those ancient collisions persist for billions of years, slowly fading but never quite disappearing. The dead are not always quiet. Many dead galaxies host active galactic nuclei, where supermassive black holes at their centers devour leftover gas. The black hole generates more energy than the entire galaxy's stars combined, creating brilliant jets of radiation and particles that shoot out thousands of light years into space. The galaxy is dead, but its heart still beats with terrifying power, max 2,129 to 1, and galaxies like it force us to reconsider everything we thought we knew about how galaxies die. Death is not always violent. It can be peaceful, gradual, inevitable. A galaxy can simply run out of fuel and fade away, maintaining its structure even as its light slowly dims. Understanding how and why galaxies die helps us understand where our own Milky Way is headed. Will we die quietly, or will our collision with Andromeda in 4.5 billion years trigger one final burst of star formation before the lights go out forever? The answer to that question waits at the end of our journey. But first, we need to explore galaxies at the opposite extreme. Galaxies so massive, so enormous, that they dwarf everything around them. IC 1101 floats at the heart of the Abell 2029 galaxy cluster, 1.07 billion light-years from Earth. It is a monster beyond comprehension. 6 million light-years across, over 100 trillion stars. If IC 1101 replaced the Milky Way, its edges would extend past the Andromeda galaxy and beyond. To understand this scale, consider our own galaxy. The Milky Way stretches roughly 100,000 light-years from edge to edge, a respectable size. It contains between 200 and 400 billion stars. Our entire local group of galaxies, including Andromeda and dozens of smaller companions, fits comfortably within a region 10 million light-years across. IC 1101 alone is more than half that size. This galaxy is an elliptical, which makes sense. The largest galaxies in the universe are always ellipticals. They form at the centers of massive galaxy clusters, sitting at the bottom of enormous gravitational wells. Smaller galaxies fall toward them over billions of years, merging and adding their stars to the growing giant. IC 1101 has been cannibalizing its neighbors for ages, growing larger with each meal. The galaxy contains a central supermassive black hole weighing in at roughly 40 billion times the mass of our comparison. The black hole at the center of the Milky Way is only 4 million times that mass. IC 1101's black hole is 10,000 times heavier. The event horizon of such a monster stretches farther across than our entire planetary system. Giant ellipticals like IC 1101 represent the end state of galactic evolution in dense environments. They are fossil records of cosmic construction. Every star in that enormous structure came from somewhere else, from hundreds, maybe thousands of smaller galaxies that merged together over cosmic time. Each merger added mass. Each collision scrambled orbits. Eventually, what remained was a shapeless ball of stars, growing ever larger as more victims fell into its gravitational embrace. The surface brightness of IC 1101 is surprisingly low. All those stars spread across such an enormous volume means the galaxy appears diffuse, almost ghostly. If you could stand at the edge of IC 1101 and look inward, you would not see a brilliant concentration of stars. Instead, you would see a faint glow, stars scattered so widely that the spaces between them dominate. Other extreme giants exist, scattered throughout the universe. NGC 262, also known as Markarian 348, spans 1.3 million light-years. SO 306-17 extends even farther. A 1,689 ZD, one pushes into truly incomprehensible territory. These are brightest cluster galaxies, or BCGs, the dominant members of their respective galaxy clusters. They sit at the centers of the largest gravitationally bound structures in the universe. The formation of such giants requires specific conditions. They need to be in regions of space with high galaxy density. They need time for mergers to occur. And they need to avoid major interactions that would disrupt their growth. Most importantly, they need to be patient. Building a galaxy 6 million light-years across takes tens of billions of years. IC 1101 has been growing since the early universe, accumulating mass merger by merger, collision by collision. The stellar populations in these giants tell a story of violence. When galaxies merge, their stars almost never collide directly. Space between stars is so vast that even in a galactic collision, individual stars pass by each other like ghosts. However, the gas clouds within merging galaxies do collide. They crash together at speeds of hundreds of miles per second, shocking and compressing. This triggers intense bursts of star formation, creating massive blue stars that burn bright and die young. IC 1101 shows no signs of recent star formation. Its light comes from old, cool stars, red giants, and yellow dwarfs that have been burning steadily for billions of years. This indicates the galaxy has not experienced a major gas-rich merger recently. All its cannibalistic meals have been dry mergers, consuming galaxies that had already exhausted their gas supplies. The halo surrounding IC 1101 extends even farther than the visible galaxy. This halo contains globular clusters, ancient balls of stars that orbit the galaxy in the darkness. Normal galaxies might have a few hundred globular clusters. The Milky Way has about 150. IC 1101 has tens of thousands. Each one is a relic from a long-dead galaxy that was torn apart and absorbed. Measuring the mass of IC 1101 is challenging. The visible stars account for only a fraction of the total mass. Dark matter dominates. This invisible substance, which interacts only through gravity, forms a massive halo around the galaxy. The total mass, including dark matter, likely exceeds 30 trillion times the mass of our star. Most of that mass is completely invisible, detectable only through its gravitational effects on surrounding objects. At the opposite extreme from these, giants are ultra-compact dwarf galaxies. These strange objects contain billions of stars packed into regions only a few hundred light-years across. They may be the stripped cores of larger galaxies that ventured too close to a giant like IC 1101 and had their outer layers torn away by tidal forces. What remains is the dense nucleus, a galaxy reduced to its most essential core. The size range of galaxies spans 6 orders of magnitude, from dwarf galaxies a few hundred light-years across to monsters like IC 1101 stretching millions of light-years. From galaxies containing only a few million stars to those with over 100 trillion, this incredible diversity emerges from the same basic physical processes: gravity, star formation, mergers, dark matter. Yet the outcomes vary wildly depending on environment and history. IC 1101 will continue growing. It sits at the bottom of its galaxy cluster's gravitational potential, meaning everything else in the cluster is slowly falling toward it. Over the next hundreds of billions of years, it will consume more neighbors. It will grow larger. Eventually, it may merge with other giant ellipticals in nearby clusters to form something even more enormous. The far future of the universe will be dominated by objects like IC 1101. As dark energy continues to accelerate cosmic expansion, galaxy clusters become isolated from each other. Each cluster evolves independently. Within each cluster, galaxies merge together. The final state, trillions of years from now, will be single giant elliptical galaxies, one per cluster, floating alone in an expanding void. IC 1101 gives us a preview of that distant future. Understanding the largest galaxies helps us understand how structure forms in the universe. These giants mark the most massive gravitationally bound objects that will ever exist. They represent the limits of cosmic construction. Nothing larger will have time to form before dark energy tears the universe apart. But size is not the only extreme. Galaxies can be violent, destructive, capable of tearing each other apart in cosmic collisions that last for hundreds of millions of years. 2 galaxies approach each other, each containing hundreds of billions of stars. They are moving at hundreds of miles per second. The collision is inevitable, and when they finally merge, almost no stars will touch. This seems impossible. 2 enormous structures, each packed with stellar matter, passing through each other completely. Yet this is exactly what happens during galactic collisions. The reason lies in the fundamental nature of space itself. Stars are tiny points separated by mind-boggling distances. Consider the Milky Way. Our nearest stellar neighbor, Proxima Centauri, sits about 4.2 light-years away. A light-year equals roughly 6 trillion miles. The space between us and that neighboring star is almost entirely empty. Vacuum, darkness. If you scaled our star down to the size of a grain of sand, the nearest other grain of sand would be 4 miles away. When 2 galaxies collide, their stars pass through like bullets through fog. The probability of any 2 stars actually striking each other is astronomically small. Imagine throwing 2 handfuls of sand at each other. A few grains might collide, but most will fly past without touching. Galactic collisions work the same way, except the distances between grains are millions of times larger. What does collide, however, is the gas. Galaxies contain vast clouds of hydrogen gas floating between the stars. These clouds are diffuse, but they are enormous, light-years across, thousands of times the mass of individual stars. When 2 galaxies merge, their gas clouds slam into each other at tremendous velocities. The collision creates shock waves that heat the gas to millions of degrees. The shock wave also compresses the gas, squeezing it down until gravity takes over and triggers star formation. This is why merging galaxies often appear brilliant blue. The collision ignites furious bursts of stellar birth. Thousands of new stars form every year. These newborn stars are massive, hot, and blue. They flood their surroundings with ultraviolet radiation, making the gas clouds glow in spectacular colors. Pink emission nebulae mark regions where hydrogen is ionized by intense starlight. Blue regions indicate young stellar populations. The antennae galaxies provide a perfect example. Two spiral galaxies in the process of merging, about 45 million light-years from Earth. Long tails of stars and gas stream away from the collision site, resembling insect antennae. These tails form because gravity stretches and distorts both galaxies. Stars on the outer edges get flung outward into sweeping arcs, hundreds of thousands of light-years long. Within the collision zone, the two galactic cores orbit each other, gradually spiraling inward. This process takes hundreds of millions of years. Friction from the gas clouds robs the cores of energy, causing them to sink deeper into the merged system. Eventually, the cores will coalesce into a single, larger nucleus. The two supermassive black holes will merge, releasing gravitational waves that ripple through space-time itself. Computer simulations of galactic collisions reveal intricate details impossible to observe directly. The mergers take so long that we can only ever see snapshots. One collision frozen at the moment when tidal tails first form, another caught just as the cores begin their final spiral. Simulations let us watch the entire process unfold, from first approach through final merger. These simulations show that the orientation and relative velocities of colliding galaxies determine the outcome. A head-on collision produces a different result than a glancing blow. Galaxies approaching at different angles create different patterns of tidal distortion. Fast collisions pass through quickly, causing minimal disruption. Slow collisions allow gravity more time to work, creating dramatic tidal features. The Mice galaxies show another collision in progress. Two spiral galaxies with long, thin tails of stars pulled out behind them. The tails curve in opposite directions, making the system resemble two mice connected by their tails. This particular merger is relatively young. The galaxies have made one close pass and are now separating before gravity pulls them back for another encounter. Multiple passages are common in galactic mergers. Two galaxies rarely collide once and stick together. Instead, they pass through each other, separate, then fall back together again. Each passage scrambles their structures a bit more. Stars get redistributed into larger orbits. Gas clouds collide and trigger more star formation. After several passages, the two galaxies are so thoroughly mixed that they effectively become one. The final product of a major merger depends on the masses involved. Two similar-sized spiral galaxies typically produce an elliptical. The ordered rotation of both spirals gets scrambled into random motions. The merger consumes all available gas in a final burst of star formation, leaving behind a gas-poor elliptical dominated by old stars. This is how astronomers believe most elliptical galaxies form. Minor mergers, where a large galaxy consumes a much smaller companion, produce different results. The large galaxy usually survives relatively intact. It might gain some new stars, develop a slight warp in its disk, or show tidal streamers for a while, but its basic structure persists. The small galaxy gets completely destroyed, torn apart by tidal forces, and absorbed. Our own Milky Way is currently experiencing a minor merger. The Sagittarius dwarf elliptical galaxy is being ripped apart as it orbits through our galactic disk. Streams of stars from this doomed galaxy wrap around the Milky Way like ribbons. The merger has been ongoing for hundreds of millions of years. Eventually, nothing will remain of Sagittarius except its stars, scattered among our own. Dark matter plays a crucial role in galactic collisions. The dark matter halos surrounding each galaxy are much larger than the visible portions. These halos collide first, before the stars and gas. The gravitational interaction between dark matter halos determines the trajectories and outcomes of mergers. Without dark matter, galactic collisions would look completely different. Some collisions create spectacular structures that persist for millions of years before fading. Tidal tails, shells of stars, ripples in galactic disks. These features mark the violence of past interactions. They gradually disperse as stars drift into new orbits, But for a brief cosmic moment, they create some of the most beautiful structures in the universe. The collision rate was much higher in the early universe. When the cosmos was younger and smaller, galaxies were packed more closely together. Mergers happened frequently. This violent past shaped the galaxy population we see today. Many large galaxies show evidence of ancient mergers in their structure and stellar populations. Understanding collisions helps us predict our own future. The Andromeda Galaxy is approaching the Milky Way at about 70 miles per second. In approximately 4.5 billion years, the collision will begin. Our night sky will transform as Andromeda grows larger, eventually dominating the view. The merger will trigger intense star formation. It will scramble both galactic structures, and ultimately, it will create a giant elliptical galaxy that astronomers have already nicknamed Milkomeda. When that collision happens, Earth itself has little to fear from stellar impacts. The odds of another star hitting our planetary system are infinitesimally small. The greater danger comes from gravitational disruption. Our orbit around the galactic center might change. We could be flung into the outer halo or drawn closer to the merged core. Either way, our position in the galaxy will shift dramatically. But before we reach that violent future, we need to understand a process already underway: cannibalism. Some galaxies do not wait for collisions. They actively hunt and consume their neighbors. Andromeda has been eating other galaxies for at least 10 billion years. Evidence of its cannibalism surrounds it like a crime scene. Streams of stars, shells of debris, the shredded remains of dozens of smaller galaxies scattered through its halo. Researchers discovered this by studying the motions of stars in Andromeda's outer regions. They found groups of stars all moving in the same direction at the same speed. These coherent streams mark the remnants of satellite galaxies that ventured too close. Andromeda's gravity grabbed them, stretched them, and tore them apart. Now their stars orbit the larger galaxy, spread out along elongated paths that trace their final moments as independent objects. The most recent meal happened between 1 and 3 billion years ago. A galaxy containing hundreds of millions of stars fell into Andromeda. Tidal forces ripped it apart, scattering its stars across thousands of light years. Some stars were flung into the outer halo. Others crashed through Andromeda's disk, creating ripples that persist to this day. The event left permanent scars in Andromeda's structure. Cannibalism is different from collision. When two similar-sized galaxies collide, they merge. Neither really consumes the other. They combine into something new. Cannibalism happens when a large galaxy encounters something much smaller. The size difference is so extreme that the smaller galaxy has no chance of survival. It gets ripped apart and absorbed, adding its mass to the larger galaxy without fundamentally changing its structure. The Milky Way is also a cannibal. We are currently consuming the Sagittarius dwarf elliptical galaxy. This small galaxy, containing only a few billion stars, has been orbiting through our disk for hundreds of millions of years. Each passage through the dense inner regions of the Milky Way strips away more stars. Long streams of stellar debris wrap around our galaxy like ribbons. In another few billion years, Sagittarius will be completely gone, its stars indistinguishable from our own. The large and small Magellanic Clouds will suffer the same fate. These irregular galaxies, visible to the naked eye from the southern hemisphere, are satellite galaxies of the Milky Way. They orbit us at distances of roughly 160,000 light-years. Gravity is slowly pulling them closer. Eventually, they will fall in and be torn apart. Their stars will join ours. Their gas will trigger new bursts of star formation. Nothing will remain of them as independent galaxies. Cannibalism leaves distinctive signatures. When a small galaxy is consumed, its stars do not immediately mix with the host galaxy's stellar population. They remain in coherent streams for billions of years, following the same orbital path their original galaxy took. These streams can be detected by carefully measuring the positions and velocities of individual stars. Stars from different streams have different motions, allowing astronomers to reconstruct which satellite galaxy they came from. The galactic halo is essentially a graveyard of cannibalized galaxies. Every large galaxy has a halo, a diffuse sphere of stars extending far beyond the visible disk. Most halo stars are old and metal-poor, having formed in the early universe. They orbit in random directions, creating a spherical cloud around the galactic center. Analysis shows that many halo stars originally belonged to smaller galaxies that were consumed long ago. Some galaxies are professional cannibals, consuming dozens or even hundreds of smaller neighbors. Giant elliptical galaxies at the centers of galaxy clusters are the worst offenders. They sit at the bottom of deep gravitational wells, patiently waiting as smaller galaxies fall toward them. The cluster environment is crowded, with hundreds or thousands of galaxies packed into a relatively small volume. Interactions and mergers are common. The central giant grows steadily larger, fed by an endless stream of victims. Centaurus A provides a dramatic example. This giant elliptical galaxy shows clear evidence of recent cannibalism. A thick dust lane cuts across its center, the remnant of a spiral galaxy it consumed within the last few 100 million years. Jets of material shoot outward from the central supermassive black hole, powered by the influx of gas from the merger. Radio observations reveal enormous lobes, extending millions of light-years beyond the visible galaxy, inflated by these jets. The process of tidal disruption is brutal. As a small galaxy approaches a larger one, the near side experiences stronger gravity than the far side. This difference in gravitational pull creates tidal forces that stretch the smaller galaxy. Stars on the leading edge get pulled forward. Stars on the trailing edge lag behind. The galaxy elongates, transforming from a compact sphere into a long, thin stream. If the small galaxy is diffuse enough and the tidal force is strong enough, it can be completely destroyed in a single pass. More commonly, the process takes multiple orbits. Each pass strips away some stars. The small galaxy gradually loses mass, becoming smaller and fainter. Eventually, only the dense core remains. In some cases, even the core is destroyed, leaving nothing behind except scattered stars. Globular clusters often survive this process better than the galaxies that host them. These dense balls of old stars are tightly bound by gravity. When their parent galaxy is torn apart, globular clusters can remain intact, continuing to orbit the larger galaxy long after their original home is destroyed. This is why giant galaxies often have vast collections of globular clusters. Many of them are orphans, inherited from cannibalized victims. The rate of cannibalism was higher in the past. The early universe was more compact, with galaxies packed more closely together. Small galaxies fell into larger ones frequently. This hierarchical merging, where small structures combine to form larger ones, represents a fundamental aspect of cosmic structure formation. Everything starts small. Gravity pulls small things together. They combine, grow larger. The process repeats. Eventually, you get giant galaxies, like the Milky Way and Andromeda. Cannibalism will increase in our future. Andromeda is approaching us. In 4.5 billion years, we will collide. During that collision, many of both galaxies' satellite systems will be destroyed. The gravitational chaos will send small galaxies careening into the merging core. Some will be torn apart by tidal forces. Others will trigger starbursts as their gas crashes into existing clouds. The final merged galaxy will be larger, more massive, and surrounded by debris fields, marking the destruction of dozens of smaller companions. This process is not unique to our corner of space. It is happening everywhere in the universe. Every large galaxy has consumed smaller neighbors. Every galaxy cluster contains cannibals at its center, steadily growing larger. The night sky is a battlefield where gravity slowly but inexorably pulls structure together, destroying the weak and feeding the strong. The victims of cannibalism are not always helpless, however. Sometimes they fight back. a gas-rich dwarf galaxy falling into a larger galaxy can trigger intense bursts of star formation in both systems. The merger might destabilize the larger galaxy's disk, creating warps and asymmetries. In rare cases, the interaction can even reignite star formation in a dead galaxy, bringing it temporarily back to life before it fades again. Ultra-faint dwarf galaxies represent the faintest, smallest galaxies known. They contain only a few thousand stars, barely more massive than globular clusters. These objects are incredibly difficult to detect because they are so dim. Many of them orbit as satellites around larger galaxies, waiting to be consumed. Studying them helps us understand what the building blocks of larger galaxies look like. Every giant galaxy is made from hundreds or thousands of smaller pieces, merged together over cosmic time. The ultimate fate of most small galaxies is to be eaten. Only those far from larger neighbors stand a chance of survival. Isolation is the only defense against cannibalism. Everything else eventually falls into a gravitational well and gets torn apart. This is the brutal logic of cosmic structure formation. Gravity does not care about beauty or complexity. It simply pulls, and the small inevitably fall toward the large. Yet, even as cannibalism destroys some galaxies, it occasionally creates something unexpected. Sometimes, the physics goes wrong in the most spectacular way possible. Sometimes, galaxies lose something they should never be able to lose. NGC 1052 DF2 should not exist. This galaxy, located 65 million light-years from Earth, appeared to contain almost no dark matter at all. The discovery sent shockwaves through the astronomy community. Every galaxy contains dark matter. Dark matter outweighs visible matter by 5 to 1 in most galaxies. It forms the gravitational scaffolding around which normal matter organizes. Without dark matter, galaxies should not be able to form or hold together. Yet there it was, a galaxy with the mass of visible stars, matching the observed gravitational behavior. No invisible mass, no dark matter halo, nothing but stars and a small amount of gas. The finding challenged fundamental physics. Dark matter is not optional. It makes up roughly 85% of all matter in the universe. It shaped the cosmic web. It allowed the first galaxies to form. Its gravitational influence controls how galaxies rotate, how they cluster, and how they evolve. Finding a galaxy without it was like finding a building without a foundation. Scientists immediately questioned the result. Maybe the distance measurement was wrong. If the galaxy was closer than calculated, the mass estimates would change. Maybe tidal interactions had stripped away the dark matter halo. Maybe we were looking at a rare, temporary state before dark matter fell back in. 1 year later, researchers solved the mystery. The galaxy was not 65 million light-years away. It was closer, only 42 million light-years distant. That change in distance completely altered the mass calculations. When astronomers recalculated using the correct distance, dark matter reappeared. NGC 1052 DF2 does have a dark matter halo after all, just a smaller one than originally thought. The relief in the scientific community was palpable. The laws of physics remained intact. Dark matter was still required for galaxy formation. The universe made sense again. But the episode raised important questions. Could galaxies exist without dark matter under certain circumstances? Are there genuine exceptions to the rule? Theoretical models suggest that in extremely rare cases, tidal forces might be able to strip dark matter away from a galaxy. Dark matter interacts only through gravity. It does not feel electromagnetic forces. This means it cannot be compressed or heated like normal matter. In a strong tidal field, dark matter particles might be pulled away from a galaxy more easily than stars and gas. Imagine a small galaxy falling through a massive galaxy cluster. The cluster's gravitational field creates enormous tidal forces. As the small galaxy passes through, its dark matter halo gets stretched and distorted. Dark matter on the outer edges is pulled away. the halo shrinks. If the tidal forces are strong enough and the passage close enough, most or all of the dark matter could be stripped away, leaving behind a galaxy made purely of normal matter. This process might explain ultra-diffuse galaxies, strange objects that are as large as the Milky Way but contain 100 times fewer stars. Some of these galaxies appear to have very little dark matter relative to their size. They are diffuse, spread out, almost ghostly. Their dark matter halos may have been partially stripped by tidal interactions, leaving behind puffed-up collections of stars with insufficient gravity to pull them into compact structures. Studying galaxies with unusual dark matter content helps us understand what dark matter actually is. We know it exists because we see its gravitational effects. Galaxies rotate too fast. Galaxy clusters hold together despite insufficient visible mass. Gravitational lensing bends light around invisible matter, but we do not know what particles make up dark matter. We cannot detect them directly. We can only infer their presence through gravity. If we could find a galaxy genuinely lacking dark matter, it would tell us something crucial. It would mean dark matter and normal matter can be separated. This separability would rule out certain alternative theories of gravity. Some scientists have proposed that there is no dark matter at all, that instead, our understanding of gravity needs modification on cosmic scales. Finding galaxies with different dark matter content would strongly support the existence of dark matter as actual particles rather than a modification of gravitational laws. The search continues. Astronomers are looking for more galaxies with unusual dark matter properties. They are measuring rotation curves, analyzing stellar motions, and using gravitational lensing to map dark matter distributions. Each new discovery adds to our understanding. Dark matter makes up the skeleton of the universe. It formed the structure on which everything else hangs. In the early universe, dark matter began clumping together first because it does not interact with radiation. Normal matter was coupled to light, unable to collapse while the universe remained hot and dense. Only after the universe cooled enough for atoms to form could normal matter begin falling into the gravitational wells created by dark matter. This means the cosmic web, the largest scale structure in the universe, is fundamentally a dark matter web. Filaments of dark matter stretch between galaxy clusters. Galaxies form where these filaments intersect. Voids exist where dark matter is sparse. Everything we see is just the visible fraction of a much larger, invisible architecture. Within individual galaxies, dark matter dominates the mass budget. A typical spiral galaxy's rotation curve stays flat, or even rises as you move outward from the center. This indicates that mass continues increasing with distance, even beyond where visible stars end. That invisible mass is dark matter. The halo extends far beyond the optical disk, creating a gravitational potential well that holds everything together. Without dark matter, the outer regions of spiral galaxies would rotate too slowly. Stars would drift away. The galaxy would fly apart. The fact that galaxies remain stable over billions of years is powerful evidence that dark matter exists and that it holds them together. Giant elliptical galaxies provide another test. These galaxies have very little gas and dust. Their mass is almost entirely in stars and dark matter. By measuring the velocities of stars throughout the galaxy, astronomers can map the dark matter distribution. The results consistently show that dark matter outweighs visible matter by factors of 5 to 10. Galaxy clusters offer the strongest evidence. Clusters contain hundreds or thousands of galaxies plus vast amounts of hot gas. The gas emits X-rays, allowing its temperature and density to be measured. From those measurements, scientists can calculate how much mass is needed to hold the cluster together against its own thermal pressure. The answer is always the same. Visible matter accounts for only 15% of the total. Dark matter makes up the rest. Gravitational lensing confirms this. When light from distant galaxies passes through a galaxy cluster, the cluster's gravity bends the light, creating distorted images and multiple images of the same background galaxy. By analyzing these lensing patterns, astronomers can map the total mass distribution in the cluster. The maps always show that most mass is invisible, distributed in a smooth halo around the cluster. NGC 1052 DF2 taught us an important lesson. Extraordinary claims require extraordinary evidence. When a result contradicts fundamental physics, the first assumption should be that something is wrong with the measurement, not with physics itself. Distance errors are common in astronomy. Objects in space do not come with convenient labels telling us how far away they are. We infer distances from brightness, redshift, and other indirect measurements. All of these methods have uncertainties. The episode also demonstrated the self-correcting nature of science. When the initial result was published, dozens of research groups immediately began checking it. They looked for alternative explanations. They questioned the assumptions. They made new observations. Within a year, the error was found and corrected. The process worked exactly as it should. The quest to understand dark matter continues. Particle physicists are building detectors deep underground, shielded from cosmic rays, waiting to catch the faint signal of a dark matter particle interacting with normal matter. So far, no confirmed detection. But the search goes on. If dark matter is made of particles, we will eventually detect them. And when we do, it will revolutionize our understanding of particle physics and cosmology. Meanwhile, astronomers keep finding galaxies with strange properties. Galaxies where dark matter seems more or less abundant than expected. Each one is a puzzle to solve, a clue to how dark matter behaves and how galaxies form. Understanding the exceptions helps us understand the rule. Some galaxies challenge our expectations in a completely different way. They have shapes that should not be possible, structures so bizarre that scientists are still trying to explain how they form. Hoag's object hangs in space like a cosmic donut. A bright yellow cluster of old stars forms the center. Surrounding it, separated by a gap of apparent emptiness, a perfect blue ring of younger stars circles at a distance. The symmetry is uncanny. The separation between core and ring is clean, precise. It looks artificial, but Hoag's object is completely natural. It is one galaxy, not two. Approximately 600 million light-years from Earth, classified as a ring galaxy, though even that term does not adequately capture its strangeness. Ring galaxies are rare. Fewer than one in every 1,000 galaxies shows this structure. The formation mechanism is not completely understood. Several theories exist, but none perfectly explains every observed ring galaxy. Each example seems to form through slightly different circumstances. The most common explanation involves collision. A small galaxy passes directly through the center of a larger disk galaxy. The collision creates a ripple, like dropping a stone into a pond. The ripple propagates outward through the larger galaxy's disk. Gas and stars move with the ripple, compressing and triggering star formation. This creates a ring of young blue stars, expanding away from the impact site. The problem with this theory for Hoag's object is the lack of a visible impactor. If another galaxy caused the ring, where did it go? Simulations show that the colliding galaxy should still be visible, either embedded in the central core or passing through on the other side. Yet no such galaxy appears in observations. The mystery remains unsolved. Another theory suggests that ring galaxies form from bars. Many spiral galaxies have bars, straight structures of stars cutting across their centers. The ends of bars are locations where gas accumulates and star formation occurs. Under certain circumstances, a bar might become unstable and dissolve. When it does, the material at the ends could be flung outward, creating a ring. This explanation works better for some ring galaxies than others. Hoag's object shows no evidence of a past bar. The central region is smooth and featureless, dominated by old red stars. If a bar existed, it disappeared completely without leaving traces. Cartwheel Galaxy provides a clearer case. This ring galaxy shows obvious signs of collision. A smaller galaxy punched directly through its disk, creating spectacular ripples. Two distinct rings are visible. An inner ring where the collision triggered intense star formation, an outer ring expanding at the edge of the shock wave. Between them, the disk appears relatively empty, with material swept into the rings by the passing density wave. The outer ring of Cartwheel Galaxy is forming stars at an incredible rate. Billions of new stars have ignited in the last few 100 million years. The ring glows brilliant blue, lit by massive young stars. As these stars age and die in supernova explosions, they will enrich the surrounding gas with heavy elements, seeding future generations of star formation. The collision that created Cartwheel happened roughly 200 million years ago. The impacting galaxy has moved away, no longer visible in the immediate vicinity. The rings will continue expanding for hundreds of millions more years, gradually slowing as they plow through the intergalactic medium. Eventually, the rings will fade. The galaxy will settle into a new equilibrium, probably an irregular or elliptical structure. Lindsay-Shapley ring is another example, though smaller and fainter than Hoag's object or Cartwheel. It has a compact nucleus, surrounded by a bright ring of star formation. The ring is lopsided, thicker on one side than the other, suggesting an off-center collision or interaction with a nearby companion. Ring galaxies challenge our understanding of galactic stability. Galaxies are dynamic systems, constantly evolving. Stars orbit the center. Gas clouds collapse to form new stars. Spiral arms rotate. Everything is in motion. Ring structures represent perturbations to that motion. Something has disturbed the normal flow, creating a coherent wave moving through the galaxy. The timescales matter. A ring takes hundreds of millions of years to form and expand. During that time, differential rotation should smear it out. Stars at different distances from the galactic center orbit at different speeds. This should destroy any coherent structure quickly. Yet rings persist far longer than simple calculations predict. Something must be stabilizing them. Dark matter may play a role. The dark matter halo surrounding each galaxy creates a gravitational potential well. This potential well shapes how stars and gas move. Rings might form at specific radii where the rotation curve has certain properties, or dark matter might dampen disruptive influences that would otherwise destroy the ring. Some ring galaxies appear to have multiple rings, concentric circles of star formation at different distances from the center. These might represent multiple collision events, though that seems unlikely. More probably, they mark different phases of the same collision. The first ring formed immediately after impact. Later rings developed as the disturbance propagated outward through different layers of the galactic disk. The colors of ring galaxies tell stories of stellar populations. Blue rings contain hot young stars, recently formed from compressed gas. Red or yellow cores contain older stars that formed long before the ring-creating event. The contrast between young and old, blue and red, creates stunning visual beauty, but it also provides scientific information about when star formation occurred and how the galaxy has evolved. Hoag's object remains the most enigmatic. Its symmetry is too perfect. Natural processes tend to create asymmetry, irregularity. Collisions happen at angles, not precisely head-on. Yet Hoag's object looks like it was designed by a mathematician seeking geometric perfection. The ring is circular. The core is centered. The gap between them is uniform. One peculiar detail adds to the mystery. If you look carefully at images of Hoag's object, there is another ring galaxy visible in the background, shining through the gap between core and ring. This second ring galaxy is much more distant, not physically associated with Hoag's object, but its presence creates a surreal effect. Two ring galaxies perfectly aligned, one behind the other, separated by hundreds of millions of light years. The odds of such an alignment happening by chance are extraordinarily low, yet there it is. The universe occasionally produces coincidences that would seem implausible in fiction. Understanding ring galaxies helps us understand galactic dynamics. How do galaxies respond to perturbations? What happens when you disturb a stable disk? The rings trace the propagation of density waves through galactic material. They are natural laboratories for studying collective behavior in gravitational systems. Some galaxies develop even stranger structures, not rings but bars cutting across their centers. These bars are not rare accidents. They are fundamental features affecting most spiral galaxies, including our own. 2/3 of all spiral galaxies have bars, straight structures of stars and gas cutting across their centers. The Milky Way is barred, so is Andromeda, so are the majority of spirals throughout the universe. These bars are not decorative features, they are engines that reshape galaxies. A bar forms when stellar orbits become aligned. In a normal disk galaxy, stars orbit the center in near-circular paths. Their orbits are independent, randomized, creating a smooth distribution. But under certain conditions, orbits can synchronize. Stars begin moving together in elongated paths. These coordinated motions create a density wave that manifests as a bar. The bar rotates as a solid structure. It is not made of the same stars all the time. Individual stars move in and out of the bar, but the bar itself persists. Like a traffic jam on a highway where the jam remains in place even as individual cars pass through, the bar is a pattern rather than a fixed collection of objects. Bars channel gas toward galactic centers. As gas orbits within a barred galaxy, the bar's gravity disturbs its motion. The gas loses angular momentum and spirals inward. This creates a concentration of gas near the nucleus, fueling star formation and feeding the central supermassive black hole. Barred galaxies often show intense nuclear activity because of this inward gas flow. The Milky Way's bar is roughly 27,000 light-years long. It rotates once every few hundred million years, slower than the orbital period of stars near the disk. If you could view our galaxy face-on from above, you would see a bright bar cutting across the center, with spiral arms emerging from the ends. Scientists believe bars indicate galactic maturity. Young, newly formed spiral galaxies tend to have prominent spiral arms, but no bar. As the galaxy ages and its disk settles into a more stable configuration, bars develop. The presence of a bar suggests the galaxy has completed most of its major mergers and achieved a relatively stable state. But bars are not permanent. They can form, strengthen, weaken, and dissolve over cosmic timescales. Interactions with satellite galaxies can destroy bars. Gas inflow caused by bars can eventually starve the bar itself, causing it to fade. Some galaxies show evidence of multiple bar episodes, where a bar formed, dissolved, then reformed later. NGC 1300 displays a spectacular example of a barred spiral. The bar is clear and distinct, with tightly wound spiral arms emerging from its ends. The galaxy lies about 61 million light-years away in the constellation Eridanus. High-resolution Hubble images reveal additional complexity. A smaller spiral structure exists within the bar itself, a nested pattern that defies simple explanations. The relationship between bars and spiral arms is intricate. In many barred spirals, the arms do not emerge directly from the bar's ends. Instead, there is an offset. The arms begin some distance away, connected to the bar by fainter structures. This geometry arises from the interplay between the bar's rotation and the spiral density wave. Bars also influence the overall shape of galaxy rotation curves. In a non-barred spiral, the rotation curve typically rises steeply near the center, flattens in the mid-disk, and remains flat or slowly declines in the outer regions. Barred spirals show deviations from this pattern. The bar creates non-circular motions that affect how stars move throughout the disk. Understanding these motions helps astronomers measure the masses of galaxies. By mapping velocities across the disk and accounting for the bar's influence, they can infer how much mass is present and how it is distributed. This includes both visible matter and dark matter. The formation of bars relates to disk stability. A gravitationally stable disk resists perturbations. Stars return to their original orbits after being disturbed. An unstable disk amplifies perturbations. Small irregularities grow into larger structures. Bars form when disks become unstable to bar mode perturbations, specific patterns of motion that reinforce themselves. Several factors affect disk stability. The ratio of random motions to organized rotation matters. If stars have too much random velocity, they will not maintain coherent orbits needed for bar formation. The presence of gas influences stability. Gas can cool and settle into a thin disk, making the system more prone to bar instabilities. Dark matter halos also play a role. A massive, centrally concentrated dark matter halo can stabilize the disk against bar formation. A more diffuse halo allows bars to develop more easily. This means the properties of invisible dark matter directly influence the visible structures we observe. Simulations of galaxy evolution consistently produce bars. When astrophysicists model disk galaxies over billions of years, bars form naturally in most cases. This matches observations. The majority of spirals are barred. The simulations also show that bars can dramatically alter galactic evolution. They drive gas inward, trigger starbursts, and fuel active galactic nuclei. Some galaxies have multiple bars, a large primary bar cutting across the center, and a smaller secondary bar nested inside it. These double-barred systems are uncommon but not rare. The two bars typically rotate at different rates, creating complex patterns of gas flow. Material spirals inward along the primary bar, encounters the secondary bar, and gets funneled even closer to the nucleus. The Milky Way might have a secondary bar, though observations are uncertain. We are inside the galaxy, making it difficult to map large-scale structure. Measurements of stellar positions and velocities suggest a boxy bulge near the center that could be a small bar. But confirming this requires careful analysis of incomplete data. Bars eventually drive themselves to destruction. As gas flows inward along the bar, mass accumulates near the center. This central mass concentration changes the gravitational potential. The disk becomes less susceptible to bar mode instabilities. The bar weakens and may dissolve entirely. What remains is a bulge-dominated galaxy with no bar and little remaining gas. Some elliptical galaxies show evidence of past bars, buried deep in their structure, detectable only through careful kinematic analysis, are signatures of organized motions that once belonged to a bar. These galaxies were barred spirals in the past. Mergers and evolution transformed them into ellipticals, but traces of their former structures persist. The ultimate fate of barred spirals depends on their environment. Isolated galaxies may maintain their bars for tens of billions of years. Galaxies and clusters undergo more frequent interactions that disrupt bars. Over cosmic time, the population of barred spirals evolves as some galaxies lose their bars, while others develop them. Our Milky Way's bar will probably persist for billions of years. It will continue channeling gas inward, fueling slow but steady star formation near the galactic center. When we eventually collide with Andromeda, the bar will be destroyed. The merger will scramble both disks, creating a new elliptical galaxy with no organized rotation and no bar. Understanding bars is crucial for understanding how galaxies evolve. Bars are not static decorations. They are dynamic structures that actively shape galactic evolution, controlling star formation rates, gas distributions, and nuclear activity. And some galaxies take this activity to extremes, rotating so fast that they should tear themselves apart. Max 2129 to 1 rotates twice as fast as the Milky Way. Its disk spins at speeds that seem impossible for such a massive object. 300 billion stars whirl around the center in synchronized motion. The rotation is so rapid that centrifugal force should fling stars outward into space. Yet the galaxy holds together. It has been dead for billions of years, forming no new stars, but its structure remains stable. How does it maintain such extreme rotation without flying apart? Dark matter provides the answer. The galaxy sits in a massive dark matter halo far more extensive than the visible disk. This halo creates a deep gravitational well that holds everything in place despite the high rotational velocity. Without dark matter, max 2129-1 would have disintegrated long ago. The discovery of this galaxy challenged theories of how dead galaxies form. Scientists expected that when galaxies stop forming stars, they would also stop rotating. The cessation of star formation should coincide with a transition from ordered rotation to random motions. Dead galaxies should be ellipticals with no net spin. Finding a rapidly rotating dead disk galaxy defied this expectation. Max 2129-1 is not alone. Astronomers have since found other fast-rotating dead disks. These galaxies represent a distinct evolutionary path. They formed their stars early, in a disk configuration. Then star formation stopped, but the disk survived. Instead of mergers scrambling the structure into an elliptical, these galaxies somehow maintained their rotation while going dormant. The rotation velocity of a galaxy tells us about its mass distribution. By measuring how fast stars orbit at different distances from the center, we can infer where mass is concentrated. In max 2129-1, the rotation curve stays high even at large distances from the nucleus. This indicates that mass continues to increase with radius, a clear signature of an extended dark matter halo. Compare this to the Milky Way. Our galaxy rotates at approximately 140 miles per second at the location of our planetary system. Max 2129-1 rotates about twice that speed. Stars complete orbits faster. The entire galaxy spins like a cosmic carousel operating at double speed. This rapid rotation has consequences. Stars experience stronger centrifugal forces. The disk is thinner, more compressed vertically by the need to balance rotation against gravity. The galaxy is a high-energy system, maintained in a state of rapid motion by the gravitational grip of dark matter. Other galaxies spin even faster in localized regions. Some galaxies have ultra-fast nuclear winds, material near the central black hole moving at significant fractions of the speed of light. These are not rotation velocities, but they represent another form of extreme motion within galaxies. UGC 1259. One might rotate even faster than max 2129-1, though measurements are uncertain. This galaxy shows rotation velocities approaching 300 miles per second. It is also unusual in being a hybrid between a lenticular and a spiral galaxy. Its properties place it in a transitional category, neither fully alive nor fully dead. The physics of galactic rotation connects to fundamental principles. A rotating system must have angular momentum. This angular momentum is conserved unless external torques act on the system. When a galaxy forms from a collapsing cloud of gas, any initial rotation gets amplified as the cloud contracts. A slowly rotating cloud becomes a rapidly rotating disk. The rate of rotation depends on the distribution of mass. If most mass is concentrated near the center, the outer regions rotate slowly. If mass is distributed more uniformly, rotation velocities stay high at large distances. Dark matter dominates the mass in galactic halos, so its distribution determines rotation curves. Fast rotation also affects star formation. In rapidly rotating disks, shear forces tear apart gas clouds before they can collapse to form stars. This stabilizes the disk against gravitational instability. Slower rotation allows gas clouds to survive long enough to collapse. This is part of why max 2129-1, despite its rapid rotation, forms no new stars. Any remaining gas is sheared apart by differential rotation before it can condense. The history of max 2129-1 remains mysterious. Did it always rotate this fast? Or did some events spin it up to its current velocity? Mergers can increase or decrease rotation depending on the geometry of the collision. A retrograde merger, where the infalling galaxy orbits opposite to the disk rotation, would slow down the disk. A prograde merger would speed it up. Computer simulations struggle to reproduce galaxies like Max 2129 to 1. Most models predict that dead galaxies should be slow rotators or non-rotators. Producing a fast-rotating dead disk requires fine-tuning initial conditions and evolutionary history. The rarity of such galaxies suggests they represent special cases, not the typical path of galactic evolution. Yet even these extreme rotators pale compared to objects on even smaller scales. Neutron stars, the collapsed cores of massive stars, can rotate hundreds of times per second. Their surfaces move at significant fractions of light speed. Compared to that, even Max 2129 to 1's rotation seems sedate. The key difference is scale. A neutron star is only miles across. A galaxy spans tens of thousands of light years. Rotating a structure that large at high velocity requires enormous amounts of angular momentum and gravitational force to hold it together. Understanding rotation helps us understand galactic dynamics and stability. It reveals mass distributions. It constrains evolutionary histories. And it occasionally produces visual wonders when we view rotating galaxies from just the right angle. Some galaxies, seen edge-on, create spectacular light shows. Others develop features so unusual they become landmarks in the cosmic landscape. Some even develop eyes. IC 2163 stares into space. An enormous eye, light years across, gazes outward from its disk. The pupil is dark, surrounded by a bright blue iris of young stars. The effect is uncanny, unsettling, beautiful. This is not an eye in any biological sense. It is a tidal feature, created when IC 2163 brushed past another spiral galaxy, NGC 2207. The interaction stretched IC 2163's disk, pulling stars and gas into an elongated stream that curves back on itself. Viewed from Earth, that stream creates the illusion of an eye staring back at us. The eye is temporary. Tidal features like this last only a few tens of millions of years. Already, the structure is dispersing. Gas within the eye moves at different speeds, breaking up the coherent pattern. In cosmic terms, we are witnessing a brief moment, a galactic blink. The formation of ocular features requires specific conditions. Two galaxies must pass close to each other, close enough for tidal forces to distort their disks. The relative velocities must be just right. Too fast, and the galaxies pass through without significant interaction. Too slow, and they merge completely. The geometry must align so that from Earth's perspective, the resulting tidal stream appears circular. When NGC 2207 passed IC 2163, it pulled out a long stream of stars and gas. This stream curves around the galaxy's disk in a spiral pattern. At one point, the stream aligns with our line of sight, creating the eye illusion. The dark pupil is actually a region where the stream passes in front of the disk. The bright iris is where compressed gas in the stream is forming new stars. Observations reveal the eye is racing toward IC 2163's center. Gas moves at roughly 62 miles per second, spiraling inward like water down a drain. As it approaches the galactic nucleus, the gas crashes into other material, creating shock waves. These shocks compress the gas, triggering bursts of star formation. The collision will slow the gas down. Like a wave hitting a shore, the inward-moving material decelerates as it encounters resistance. This deceleration causes gas to pile up, increasing density. Higher density means more star formation. The result is a bright ring of young stars, marking where the tidal stream dumps material into the inner galaxy. Tidal interactions are common in dense galaxy environments. Pairs of galaxies often orbit each other, making repeated close passes over hundreds of millions of years. Each passage creates new tidal features. Arms get stretched, disks develop warps, streams of stars and gas arc between the two galaxies. The mice galaxies show similar features. Two galaxies with long tails curving away from their cores. The tails are made of stars pulled out by tidal forces. They extend for hundreds of thousands of light years, marking the path of past close encounters. The antennae galaxies display even more dramatic tidal structures. Their long streamers resemble insect antennae, hence the name. These streamers contain both stars and gas. Some regions are forming new stars, lit blue by hot young stellar populations. Other regions are dark, filled with dust clouds that block light from background sources. Tidal features provide natural laboratories for studying star formation. The compressed gas in tidal streams often forms stars more efficiently than gas in undisturbed disks. This creates populations of young stars in unusual locations, far from the main bodies of the galaxies involved. IC 2163's eye will not last. The gas will disperse. New stars formed in the feature will drift into different orbits. Within 100 million years, the eye will be gone. Future observers will see only a normal spiral galaxy, perhaps with a slight asymmetry hinting at past interaction. But for now, the eye watches. It reminds us that galaxies are not static objects. They interact, collide, reshape each other through gravity's inexorable pull. Every galaxy in a group or cluster has experienced multiple close encounters. Most bear scars from those encounters, visible as warps, asymmetries, and tidal streamers. Some tidal features are far more bizarre than eyes. There are galaxies that look like jellyfish, with tentacles of gas streaming behind them. There are galaxies that resemble tadpoles, with heads and long tails. There are galaxies shaped like dolphins, penguins, and porpoises. All these shapes arise from gravity and motion. There is no mystery, no strange physics, just the interplay of gravitational forces acting on extended structures over millions of years. Yet the results can look designed, as if someone deliberately shaped these galaxies into recognizable forms. The eye of IC 2163 will close soon, at least on cosmic timescales. But other eyes will open elsewhere. The universe contains billions of galaxies undergoing interactions right now. Statistical certainty guarantees that some of them will develop features resembling eyes, faces, or other familiar shapes. We are pattern recognition machines, evolved to detect faces and meaningful shapes. When we see an eye in a galaxy, part of our brain insists there must be intent, design. But there is only physics, gravity pulling, gas compressing, stars forming. The eye is accidental, temporary, meaningless. Yet, it is also beautiful, and beauty does not require purpose to be real. Some galaxies develop structures even stranger than eyes, structures that defy our expectations about how galaxies should be organized. NGC 660 defies expectation. A disk of stars rotates in one plane. Surrounding it, a ring of stars, dust, and gas orbits in a completely different plane, nearly perpendicular to the disk. The two structures share the same center but move in different directions. This is a polar ring galaxy, one of the rarest configurations in the universe. Only about a dozen confirmed examples exist among hundreds of billions of galaxies. They should not be possible, yet there they are. The formation of polar rings requires a very specific sequence of events. A galaxy must encounter another galaxy in just the right way. The two must interact gravitationally, but instead of merging completely, the interaction tears material from one and deposits it into a polar orbit around the other. This happens so rarely that finding any polar ring galaxies is remarkable. The ring material was siphoned from a passing galaxy millions or billions of years ago. As that victim galaxy swung by, tidal forces pulled out streams of stars and gas. Those streams fell into orbit around NGC 660. But instead of settling into the same plane as the disk, they established an orbit perpendicular to it. Why perpendicular? The incoming material had angular momentum in a direction different from the disk's rotation. When it fell into orbit, conservation of angular momentum kept it in that original plane. The disk could not capture it into coplanar rotation because there was no mechanism to change the material's angular momentum vector. The result is a system with two distinct components rotating independently. The disk continues its rotation undisturbed by the ring. The ring orbits through the disk, passing above and below twice per orbit. When ring material crosses the disk plane, you might expect collisions, but space between stars is so vast that actual stellar collisions remain vanishingly rare. Gas clouds do collide when the ring passes through the disk. These collisions create shocks that compress the gas, triggering star formation. Observers see bright knots of young stars scattered along the ring, marking locations where ring gas recently crashed through disk gas. Studying polar rings helps astronomers map dark matter distributions. The ring orbits through the dark matter halo. By measuring how fast the ring rotates at different distances from the center, scientists can infer the shape of the dark matter halo. Is it spherical, elongated, flattened? The ring's motion provides clues. Results from these studies suggest dark matter halos are roughly spherical, perhaps slightly elongated. This is important because some theories predict different shapes. Constraining halo geometry constrains theories of dark matter and galaxy formation. The rings themselves are far larger than the visible disks they surround. NGC 660's ring extends well beyond where the disk fades from view. This makes sense. Tidal material gets flung outward with considerable energy. It settles into wide orbits rather than compact ones. Most polar ring galaxies are lenticular or early-type spirals. These are mature galaxies with significant bulges and settled disks. Young, actively star-forming spirals rarely show polar rings. This might indicate that polar rings form preferentially around older galaxies, or it might mean young galaxies are more likely to fully merge with companions rather than just stealing material for a ring. The lifetime of a polar ring is uncertain. Friction from gas interactions should gradually erode the ring, causing it to lose angular momentum and eventually merge with the disk. But this process takes billions of years. Many polar rings are stable over timescales comparable to the age of the universe. Some polar rings show evidence of star formation. Blue patches indicate recent stellar birth in compressed gas clouds. Other rings are redder, containing older stars with little ongoing formation. This variation suggests rings have different ages and different amounts of remaining gas. A few galaxies have multiple rings at different angles. These ultra-rare systems must have experienced multiple capture events, each adding material in a new plane. The probability of this happening is extraordinarily low. Yet a handful of examples exist, reminding us that given enough galaxies and enough time, even the most improbable events will occasionally occur. Computer simulations have successfully reproduced polar ring formation. Models show that specific collision geometries can indeed produce rings. The incoming galaxy must pass at just the right angle and speed. Too direct a collision produces a merger. Too distant a passage leaves both galaxies unaffected. The narrow range of parameters explains why polar rings are so rare. The rings also help us understand galactic cannibalism. Most cannibalism events completely destroy the victim galaxy. Material from the smaller galaxy mixes with the larger one. Nothing coherent remains. Polar rings represent cases where some structure survived. The captured material maintains an organized orbit instead of dispersing. NGC 4650A provides another beautiful example. Its ring is edge-on from our perspective, creating a spectacular visual cross. The disk appears as a horizontal band. The ring cuts vertically through it. Stars in both components are clearly visible, creating a three-dimensional effect despite the two-dimensional image. Polar rings might be more common than we realize. Some may be oriented such that from Earth, we cannot distinguish the ring from the disk. If the ring plane is only slightly tilted relative to our line of sight, it could appear as part of the disk structure. Only edge-on or near edge-on rings are obvious. This means the dozen or so confirmed polar ring galaxies might represent a small fraction of the total population. Hundreds or thousands of galaxies might have polar rings that we cannot detect due to unfavorable viewing angles. The study of these rare objects is limited by their scarcity. Each one is precious, a unique laboratory for testing theories. Astronomers compete for telescope time to observe them in detail. Every new measurement adds to our understanding. Some galaxies combine features in ways even stranger than polar rings. Galaxies where one structure hides inside another, invisible in normal light but revealed in other wavelengths. Centaurus A looks like a typical elliptical galaxy, a smooth ball of stars, faintly glowing, dominated by old stellar populations. A thick dust lane cuts across its middle, the only obvious feature disrupting the elliptical morphology. Then astronomers looked in X-rays. Hidden beneath the elliptical exterior, completely invisible in optical light, a spiral galaxy lurks. Its arms are preserved, intact, buried deep within the larger elliptical structure. This should be impossible. When galaxies merge, their structures get destroyed. Disks are scrambled into ellipticals. Spiral arms dissolve. Nothing coherent survives. Centaurus A breaks that rule. The spiral component becomes visible only when observed at specific wavelengths. X-ray and radio observations reveal its structure. The arms are deeply embedded, surrounded by the stars of the elliptical galaxy. They persist because they are made of gas and dust, not stars. The elliptical component contains almost no gas. The two structures coexist with minimal interaction. Current thinking is that Centaurus A absorbed a spiral galaxy millions of years ago. Somehow, the merger did not destroy the spiral's arms. They remained intact, preserved like fossils within the larger structure. This is the only known case where such preservation has occurred. The merger left other marks. Centaurus A is a powerful radio source. Jets of material shoot out from its central supermassive black hole, extending millions of light years into space. These jets are among the largest structures associated with any galaxy. They indicate the black hole is actively feeding on gas, likely material from the absorbed spiral galaxy. The dust lane across Centaurus A's middle is also a remnant of the merger. It marks the plane of the original spiral's disk. Dust and gas from that disk have settled into a thin lane, contrasting sharply with the elliptical's smooth distribution of stars. Star formation is occurring within the dust lane. Infrared observations reveal bright regions where gas is collapsing into new stars. This is unusual for an elliptical galaxy, which typically has exhausted its gas supply. The merger brought new fuel, temporarily reigniting stellar birth. Centaurus A is relatively close to us, only about 13 million light-years away. This proximity allows detailed study. Astronomers can resolve individual star-forming regions within the dust lane. They can map the motions of gas clouds. They can trace the structure of the buried spiral. The galaxy's central black hole weighs in at about 55 million times the mass of our star. It is one of the closest supermassive black holes to Earth, making it an excellent target for study. Observations reveal the black hole is surrounded by a warped disk of gas, fed by material falling in from the dust lane. The radio lobes extending from Centaurus A contain enormous amounts of energy. They glow from synchrotron radiation, light emitted by electrons spiraling in magnetic fields at speeds approaching light speed. These electrons were accelerated by the jets emerging from the black hole's vicinity. How did the spiral arms survive the merger? No one knows for certain. Mergers are violent events. Gas clouds collide, triggering starbursts. Tidal forces stretch and distort both galaxies. Spiral structure should be destroyed in such chaos. Yet here it persists. One possibility is that the merger was unusually gentle. Perhaps the spiral galaxy fell in along a specific trajectory that minimized disruption. Or perhaps the spiral was consumed relatively recently, and we are observing a transitional state before the arms finally disperse. Another possibility is that what we see as preserved spiral arms are actually new structures, gas that has settled into a rotating disk after the merger. This disk might have developed spiral arms through the same density wave mechanisms that create them in normal spirals. If true, then Centaurus A is not hiding an old spiral but growing a new one. Evidence suggests the merger happened between 100 million and 1 billion years ago. This is recent on cosmic timescales. The structures we observe may still be evolving toward a final stable configuration. Centaurus A is also surrounded by satellite galaxies and globular clusters. These smaller objects orbit the giant elliptical like moons around a planet. Many of them were probably captured during the merger that created Centaurus A's unusual structure. The galaxy sits at the center of the Centaurus, a galaxy group. This small cluster contains roughly 50 known galaxies. Centaurus A dominates the group, far more massive than any other member. Its gravitational influence controls the motions of surrounding galaxies. Observations across the electromagnetic spectrum reveal different aspects of Centaurus A's structure. Optical images show the elliptical component and dust lane. Infrared penetrates the dust, revealing star formation. Radio observations trace the jets. X-rays reveal hot gas and the buried spiral structure. Each wavelength contributes to a complete picture. The jets emerging from Centaurus A create radio lobes that extend far beyond the visible galaxy. These lobes are among the largest known structures associated with any active galactic nucleus. They demonstrate the enormous power output from the central black hole. Inside the nucleus, the black hole is consuming gas at a rate of about 1/10 the mass of our star per year. This may not sound like much, but the conversion of matter to energy near a black hole is incredibly efficient. Small amounts of infalling mass produce enormous energy outputs. The future of Centaurus A remains uncertain. Will the buried spiral eventually disperse, leaving a normal elliptical? Or will new gas infall from satellite galaxies maintain the spiral structure? Time will tell. Over the next billion years, continued observations by future astronomers will reveal how this bizarre system evolves. For now, Centaurus A stands as a reminder that galaxies can surprise us. Just when we think we understand how mergers work, nature produces an exception. Rules that seem ironclad turn out to have loopholes. And some galaxies combine features in ways that defy easy categorization. Other galaxies take this even further. Some spin in opposite directions within themselves, tearing at their own structure with internal conflict. M64 rotates against itself. The inner region spins in one direction. The outer region, a massive cloud of gas and dust, spins the opposite way. The counter-rotating systems meet at a boundary roughly 40,000 light-years from the center. There, gas clouds moving in opposite directions collide at hundreds of miles per second. This is the Evil Eye Galaxy, though its official designation is Messier 64. The name comes from a distinctive dark dust lane that creates the appearance of a black eye. But the real strangeness lies in the contra-rotation. How does a single galaxy end up spinning in two directions? The most likely explanation is a merger. About 1 billion years ago, M64 absorbed another galaxy. That victim galaxy had rotation opposite to M64's own. Instead of the two rotations cancelling out or mixing into random motions, they remained separate. The inner stars, which belonged to the original M64, continue their rotation. The outer gas, which came from the absorbed galaxy, keeps rotating the opposite way. The collision zone where the two systems meet is a region of intense star formation. Gas clouds moving in opposite directions slam into each other head-on. The collisions compress the gas, triggering the collapse of molecular clouds into new stars. The result is a ring of active star formation at the boundary between the counter-rotating regions. This star formation is consuming the gas rapidly. At the current rate, the outer gas reservoir will be exhausted within the next few 100 million years. When that happens, star formation will cease in the outer regions. The galaxy will settle into a quieter state, with only the inner regions continuing to form stars at a reduced rate. M64 lies about 17 million light-years from Earth in the constellation Coma Berenices. It is close enough that large amateur telescopes can observe it. The dark dust lane is visible in moderate-sized instruments, but detecting the counter-rotation requires spectroscopic observations beyond the reach of amateur equipment. The discovery of contra-rotation in M64 came from measurements of Doppler shifts. Light from gas moving toward us is blue-shifted. Light from gas moving away is red-shifted. By mapping these shifts across the galaxy's disk, astronomers determined that the outer regions are rotating opposite to the inner regions. This type of structure is rare, but not unique. A small number of other galaxies show similar contra-rotation. All of them are thought to have formed through mergers, with galaxies having opposite rotation. The key requirement is that the merger must not completely scramble the structure. Some organized motion must survive. The collision zone in M64 glows red and pink. The red color comes from hydrogen emission, ionized by ultraviolet light from newly formed stars. The pink indicates a mix of hydrogen emission and light from the young stars themselves. This creates a visually striking feature, a bright ring encircling the darker inner disk. Measuring the masses of the counter-rotating components is challenging. Standard techniques for inferring mass from rotation velocities assume the entire galaxy rotates in the same direction. When parts rotate opposite to each other, the equations become more complex. Astronomers must carefully model both components separately. Results suggest the outer counter-rotating gas contains roughly 10% of the total mass of gas in M64. The inner regions hold the majority. This makes sense if the outer gas came from a smaller galaxy absorbed by the larger M64. The victim contributed gas, but not enough to dominate the total budget. The dark dust lane that gives M64 its evil eye appearance is part of the inner region. It rotates with the inner disk, not with the outer counter-rotating gas. The dust absorbs light from stars behind it, creating the dark band visible in optical images. This dust is relatively cool, only a few tens of degrees above absolute zero. It emits primarily in the infrared, where it can be studied in detail by infrared telescopes. The dust contains complex organic molecules, building blocks that might eventually become incorporated into planets if stars form in the region. The supermassive black hole at M64's center weighs approximately 10 million times the mass of our star. This is smaller than the black hole in the Milky Way's center, which is about 4 million solar masses. Wait, that comparison is backward. M64's black hole is larger, not smaller. Regardless, the black hole is relatively quiet. It is not currently feeding actively, so there are no brilliant jets or intense radiation from the nucleus. The future of M64 is predictable. The counter-rotating gas will continue colliding, forming stars. As the gas is consumed, star formation will decline. Eventually, all the gas will either turn into stars or be blown away by stellar winds and supernova explosions. What remains will be an ordinary spiral galaxy with no counter-rotation and little ongoing star formation. Some computer models suggest the merger that created M64's current state happened relatively recently, within the last billion years. The gas has not had time to settle into a single rotating disk. Given a few more billion years, tidal friction and gas interactions would eventually align the rotation. But for now, M64 exists in a transitional state, spinning against itself. The existence of counter-rotating galaxies helps us understand how mergers unfold. Not every merger immediately creates a featureless elliptical. Some produce intermediate states that persist for billions of years. During these long transitions, galaxies can exhibit bizarre properties unlike any normal spiral or elliptical. M64 is not the most violent example of galactic peculiarity. Some galaxies undergo explosions so frequent and powerful that they seem to be tearing themselves apart. M83 is exploding. 8 supernovas are currently active in this galaxy. Remnants of hundreds more litter its disk. New stars form at a furious rate, live fast, and die young in spectacular explosions that outshine entire galaxies for weeks. This is the southern Pinwheel Galaxy. Its vibrant pink and purple colors mark regions of intense star formation. Massive stars ignite, burn through their fuel in just a few million years, then explode as supernovas. The cycle repeats continuously, driven by an abundant supply of gas and ongoing compression of molecular clouds. Why does M83 explode so often? The answer lies in its star formation rate. The galaxy is forming new stars about 10 times faster than the Milky Way. More new stars means more massive stars. Massive stars have short lifespans. They race through their life cycles and explode as supernovas. The high star formation rate directly leads to a high supernova rate. The galaxy contains vast reserves of hydrogen gas, the raw material for star formation. This gas is distributed throughout the disk in enormous clouds. These clouds are collapsing under their own gravity, fragmenting into smaller clumps that will become individual stars. The process is ongoing, continuous, self-sustaining. M83 lies about 15 million light-years from Earth, in the constellation Hydra. It is one of the brightest galaxies in the southern sky, easily visible in small telescopes. Its spiral structure is clear and well-defined. Multiple arms curve outward from a bright central bulge. The pink color that dominates M83's spiral arms comes from hydrogen emission. Young, massive stars produce enormous amounts of ultraviolet light. This UV radiation ionizes surrounding hydrogen gas, stripping electrons from atoms. When electrons recombine with hydrogen nuclei, they emit light at specific wavelengths, primarily in the red part of the spectrum. This creates the characteristic pink glow of star-forming regions. Supernova remnants appear as expanding bubbles in M83's disk. These bubbles are shells of gas blown outward by supernova explosions. They sweep up surrounding material, creating dense shells where new stars can form. This creates a feedback loop. Supernovas trigger new star formation. The new stars eventually explode as supernovas, triggering more star formation. This feedback can both enhance and suppress star formation depending on circumstances. On small scales, supernova shocks compress gas and trigger collapse. On larger scales, supernovas heat gas and blow it out of the galaxy entirely, removing fuel for future star formation. M83 is losing some gas to supernova-driven winds. Hot gas, heated to millions of degrees by repeated explosions, escapes the galactic disk and flows into the halo. This creates a galactic fountain, where gas is expelled from the disk, but eventually cools and falls back, raining down to fuel new generations of stars. The supernova rate in M83 is roughly 1 per century. For comparison, the Milky Way experiences about 2 or 3 supernovas per century. M83 is smaller than the Milky Way, but has a higher supernova rate because its star formation is more intense. Not all supernovas are created equal. Type Ia supernovas result from white dwarf stars accreting matter from companions until they exceed a critical mass and explode. Type II supernovas are core collapse explosions of massive stars. M83 experiences both types, with Type II being more common due to the high rate of massive star formation. Each supernova releases as much energy in a few weeks as our star will emit over its entire 10 billion year lifetime. The explosion accelerates particles to near light speed. It synthesizes heavy elements in the extreme temperatures and pressures of the blast. It sends shock waves rippling through the interstellar medium. These shock waves compress gas clouds, triggering new rounds of star formation. This is how supernovas seed their own replacements. The dying stars create conditions favorable for new stellar birth. The process has continued for billions of years and will continue for billions more as long as gas remains available. M83's central bulge shows evidence of past starburst activity. The concentration of old red stars suggests that hundreds of millions or billions of years ago, the center experienced intense star formation. That burst has since faded, leaving behind aging stellar populations. The galaxy's spiral arms are where current action is concentrated. Blue light from young stars, pink emission from ionized hydrogen, dark dust lanes where dense clouds block background light. All the ingredients of active star formation are present and ongoing. Observations in infrared reveal additional star formation hidden by dust. Thick clouds of dust absorb optical light, making star-forming regions appear dark, but the dust is heated by embedded stars and glows in infrared. Infrared observations show that M83's star formation is even more vigorous than optical images suggest. The galaxy contains a supermassive black hole at its center, weighing roughly 3 million times the mass of our star. The black hole is relatively quiet, not currently feeding actively. This is typical for spiral galaxies. The black holes become active primarily during mergers when large amounts of gas are funneled into the nucleus. M83 is part of the Centaurus A M83 galaxy group. This small cluster contains the peculiar elliptical Centaurus A, along with M83 and several smaller galaxies. The group is gravitationally bound, with all members orbiting a common center of mass. Eventually, M83 will exhaust its gas supply. Star formation will decline. The rate of supernova explosions will drop. The galaxy will fade from vibrant pink and blue to quieter yellows and reds. This transition takes billions of years. For now, M83 remains one of the most actively star-forming galaxies in our cosmic neighborhood. Understanding why some galaxies explode more than others helps us understand the life cycle of cosmic structures. Galaxies are not static. They evolve, changing dramatically over billions of years. The balance between star formation, gas supply, and feedback processes determines each galaxy's appearance and activity level. But not all galaxies are local. Some lie so far away that their light has traveled for most of cosmic history to reach us. These ancient galaxies reveal what the universe looked like when it was young. GNZ11 formed when the universe was only 400 million years old. Light from this galaxy has traveled for 13.4 billion years to reach us. We see it as it was in the distant past, a small, irregular collection of stars shining in the infant cosmos. This galaxy should not exist yet. 400 million years after the Big Bang seems too early for galaxies to have assembled. The universe was still settling down from its violent beginning. Dark matter had only recently begun clumping together. Gas was just starting to cool enough to collapse into stars. Yet GNZ11 was already forming stars at a rate 25 times faster than the Milky Way. It contained roughly 1 billion stars, a respectable population for such an early time. This rapid early growth challenges our models of galaxy formation. The discovery came from deep observations by the Hubble Space Telescope. By staring at a tiny patch of sky for hundreds of hours, Hubble detected extremely faint, distant galaxies. GNZ11 appeared as a small red smudge. Its light was redshifted dramatically by the expansion of space, stretched from ultraviolet wavelengths into the near-infrared. Redshift is how we measure distance for very remote galaxies. As space expands, light traveling through it gets stretched. The faster space is expanding along the light's path, the more the light is stretched. GNZ11 has a redshift of 11.1. This corresponds to a look-back time of 13.4 billion years. Only a few hundred galaxies are known at redshifts greater than 10. These ultra-distant objects are incredibly difficult to detect. They are faint, often smaller than a single pixel in most images. Confirming their distances requires spectroscopy, measuring the exact wavelengths of light they emit. The James Webb Space Telescope has pushed the frontier even further. Webb's infrared sensitivity and large mirror allow it to detect fainter, more distant objects than Hubble. Since beginning operations, Webb has found galaxy candidates at redshifts as high as 14 or 15, corresponding to times when the universe was only 200 to 300 million years old. Some of these candidates have not yet been confirmed spectroscopically. Photometric redshift estimates, based on an object's colors in different filters, can be uncertain, but even allowing for errors, it is clear that galaxies formed earlier than many models predicted. These early galaxies are small. Most contain only tens or hundreds of millions of stars, compared to hundreds of billions in mature galaxies like the Milky Way. They are building blocks. Over cosmic time, they will merge together to form larger structures. The galaxies we see today are descendants of thousands of these small ancestors. The first stars formed even earlier, perhaps as early as 100 million years after the Big Bang. These population 3 stars were massive, metal-free objects made purely of hydrogen and helium. They burned hot and bright, dying quickly in supernova explosions that enriched their surroundings with heavier elements. No population 3 stars have been directly observed. They are too distant and too short-lived, but their influence is visible in the chemical composition of later generations. The first galaxies contain small amounts of heavy elements, indicating they formed from gas enriched by earlier stellar explosions. The cosmic dark ages is the period between the Big Bang and the formation of the first stars. During this time, the universe was filled with neutral hydrogen gas. No stars shone, no galaxies existed. The cosmos was truly dark, illuminated only by the fading glow of the Big Bang itself. The first stars ended the dark ages. Their ultraviolet radiation ionized surrounding hydrogen, creating bubbles of ionized gas. These bubbles grew and merged. Eventually, the entire universe was reionized. This epoch of reionization occurred roughly between 150 million and 1 billion years after the Big Bang. Studying the most distant galaxies helps us understand reionization. These galaxies produced the UV radiation that reionized the universe. By counting how many early galaxies exist and measuring their star formation rates, we can estimate how much ionizing radiation they produced. Results suggest that small, faint galaxies were the primary drivers of reionization. Large galaxies were rare in the early universe. Most star formation occurred in dwarf galaxies too faint for current telescopes to detect individually, but collectively, these dwarfs produced enough UV radiation to ionize all the hydrogen in space. The oldest galaxies also provide tests of cosmology. The age of the universe can be calculated from expansion rate measurements. Currently, the universe is 13.8 billion years old. Finding galaxies that formed when the universe was only a few hundred million years old confirms this timeline. Some early Webb observations initially suggested galaxies at extremely high redshifts, so distant that they would have formed impossibly early. These candidates, if confirmed, would challenge standard cosmology. However, most turned out to be at lower redshifts than initially estimated, or they proved to be other types of objects misidentified as distant galaxies. The search for the earliest galaxies continues. Each new discovery pushes our understanding of cosmic history. Future telescopes will detect even fainter objects, perhaps revealing the very first galaxies to light up after the Dark Ages. These ancient galaxies are also rare. Not all of them survived to the present day. Many merged with neighbors, their stars absorbed into larger structures. A few may have been disrupted by tidal interactions and completely destroyed. The galaxies we see in the local universe are survivors, the winners of billions of years of galactic evolution. Understanding the earliest galaxies helps us understand our own origins. The Milky Way formed from mergers of smaller galaxies, like these ancient objects. Our planetary system's atoms were forged in stars that lived and died billions of years ago. We are connected to those first galaxies through an unbroken chain of stellar birth, death, and rebirth. But Webb has found stranger things than merely old galaxies. It has discovered galaxies that break our understanding of how stars and gas should behave. GSND G9422 glows with impossible light. The gas surrounding its stars shines brighter than the stars themselves. This should not happen. Stars are the light sources. Gas merely reflects or re-emits that light. Yet in this galaxy, the gas is the dominant source of illumination. The discovery came from James Webb Space Telescope observations. Astronomers were studying galaxies in the early universe, about 1 billion years after the Big Bang. Most early galaxies show predictable spectra. Light from stars with emission lines from ionized gas overlaid, GSND G9422 spectrum, look nothing like that. The emission lines were extraordinarily strong, far stronger than could be explained by normal stellar populations. The gas was emitting so much light that it outshone the stars by a significant factor. No known type of galaxy does this. The explanation involves extreme star formation under unusual conditions. The galaxy is forming massive, super-hot stars. These stars are hotter than any we see in the local universe. Temperatures exceeding 140,000 degrees. Normal massive stars reach 70 to 90,000 degrees. These are different. These extreme stars produce enormous amounts of ultraviolet radiation, so much UV light that it heats the surrounding gas to incredible temperatures. The gas becomes almost as hot as the stars themselves. Hot gas emits more light, in this case, enough to dominate the galaxy's total light output. This represents a phase of galactic evolution never seen before. Researchers believe it might be the missing link between the universe's first stars and normal galaxies. Population 3 stars. The hypothetical first generation, made purely of hydrogen and helium, would have been extremely massive and hot. But GSNDG9422 is not a population 3 galaxy. Its spectrum shows too much chemical complexity. Instead, it might be what comes after population 3, a second or third generation of stars forming in gas enriched by earlier stellar explosions, but still lacking the heavy element abundance we see in modern galaxies. The stars form differently in such environments. They can become more massive, burn hotter, and produce more intense radiation. The galaxy is in the middle of an intense starburst. Millions of new stars are forming in a concentrated region. All that stellar birth happening at once creates extreme conditions. Gas density is high. Star formation efficiency is elevated. The entire system is in a temporary but spectacular state. This cannot last long. The intense radiation from the superhot stars will eventually blow away the remaining gas. Star formation will cease. The galaxy will settle into a more normal state. The window during which gas outshines stars probably lasts only a few tens of millions of years. We are fortunate to catch it during that brief phase. Finding GSNDG9422 required Webb's infrared capabilities. The galaxy is so distant that its light is redshifted into the infrared. Hubble could not have detected its unusual spectrum. Only Webb, with infrared spectroscopy, could reveal the galaxy's bizarre properties. Researchers are now searching for more galaxies like this. If GSNDG9422 represents a common phase in early galaxy evolution, there should be others. Finding a population of such galaxies would revolutionize our understanding of how the first stellar generations formed and evolved. The discovery also demonstrates how much we still do not know. The universe is 13.8 billion years old. We have been studying it intensively for barely a century. Every new instrument reveals phenomena we never predicted. Galaxies that challenge our theories. Objects that should not exist but do. GSND G9422 may be one of the strangest galaxies ever found, but it is probably not the strangest that exists. Somewhere in the vastness of space, there are surely galaxies even more extreme. Galaxies where the laws of physics create configurations we have not yet imagined. The journey through galactic diversity is far from complete. We have explored dead galaxies, spinning galaxies, colliding galaxies, and ancient galaxies. We have seen eyes and rings and polar orbits. We have found galaxies without dark matter and galaxies where gas outshines stars. Each discovery expands our understanding. Each new observation reveals more complexity in what we thought was well understood. 2 trillion galaxies fill the observable universe. We have closely studied only a tiny fraction. The next generation of telescopes will reveal countless more. Each will add to the story. Each will deepen the mystery. The cosmos is stranger than we imagine, perhaps stranger than we can imagine. And our journey is not yet finished. There are galaxies we can never see, disappearing beyond the edge of observation. There are questions about our own fate. When Andromeda arrives and reshapes everything we know, the greatest discoveries may still lie ahead, waiting in data not yet collected, in light not yet received, in galaxies not yet detected.